This paper introduces a novel approach called MVOT that enhances how multimodal large language models reason about spatial tasks. While traditional KOT uses only text for reasoning, MVOT allows models to think in both text and images, similar to how humans process information. This is particularly important for spatial reasoning tasks where pure textual reasoning often falls short. Figure 1 illustrates the evolution of reasoning approaches from simple direct prompting to more sophisticated methods. While direct prompting provides immediate answers without explanation and chain of thought shows verbal reasoning steps, MVOT takes it further by adding visual representations at each step. This creates a more complete and natural reasoning process that better reflects how humans think through spatial problems. The technical implementation of MVOT relies on advanced multimodal architecture. The system uses two separate tokenizers for processing images and text, with a novel token discrepancy loss mechanism to ensure better alignment between these modalities. The architecture allows for seamless generation of both textual reasoning steps and visual representations of the reasoning process. Figure 2 provides a comprehensive visualization of how MVOT works across 3 different tasks. In the maze task, we can see how the system tracks and visualizes the agent's position through a maze. The mini-behavior task shows more complex interactions, including picking up and moving objects. Frozen Lake demonstrates how the system handles environmental hazards and path planning. Each example shows both the verbal reasoning steps and corresponding visual states, illustrating the interleaved nature of MVOT's reasoning process. The researchers validated MVOT on 3 distinct spatial reasoning tasks, each with different levels of complexity. The training process involves carefully structured text-image pairs, and the system is evaluated not just on task performance, but also on the quality of its visual representations. The methodology includes both traditional optimization approaches and novel recursive generation techniques. The experimental results show that MVOT consistently performs well across different tasks and complexity levels. It particularly shines in more complex scenarios where traditional approaches struggle. The system maintains stable performance even as the complexity of the environment increases, showing better robustness than existing methods. The quality of visualizations generated by MVOT is significantly enhanced by the token discrepancy loss mechanism. The system generates accurate and clean visualizations with minimal redundant patterns, maintaining this quality even during recursive generation. This makes the reasoning process more interpretable and understandable. The research introduces a promising new direction in multimodal reasoning, showing how visual thinking can complement verbal reasoning in AI systems. While there are still areas for improvement, particularly in visualization efficiency and quality, the results demonstrate the potential of this approach for enhancing both performance and interpretability in complex reasoning tasks.